Yes. All right. One more point that I wanted to make before we get going here. Let me pull up the Canvas. Because all of the assignments, if you don't have a printed copy of one of the assignments, you can always get to it on Canvas. The assignment that you actually need is always linked as a PDF in the assignment page on Canvas. So let me pull up our Canvas here.
Find the actual like conversion sheet.
So that's under the resources page. So if you go down to the bottom of the home page here. So down underneath all of the week 1, week whatever, resources and study tools has a periodic table and the equation sheet right at the top there. Okay. Any other questions about the assignment so far? Okay. Some good random questions from this week then. Sure. There we go. Okay. All right. Here's some good questions here. How far? This is an interesting question. I want you to think about how you would interpret this question. How far into the research of atoms do you think people are? Like how, if you could have put a percentage close to truth, how would you, I thought that partly the phrasing was really interesting on that one. But also it is an interesting question. Is there, because in order to put a percentage to it, there has to be a start and an end, right? Because you have to have 0% and you have to have 100%. How do you define either of those? Which I thought that really wasn't a question that you could answer per se. But if you define like 0% of knowledge of science as being like maybe some form of life that doesn't even understand cause and effect, because really cause and effect is like the first piece of science, right? First step in science, understanding if I do this, then that happens. Without understanding cause and effect, you can't have science. Not all life does understand cause and effect too. But that'd be pretty early on in the evolutionary path. And 100% would have to be something like knowing every single particle and how every single type of matter interacts with every other type of matter in the universe. So putting a number to where we are along that spectrum is be kind of hard. So just to pick a number, I'd probably say 50% maybe. But that's just because I don't have a better answer. I really just thought that was an interesting question to think about. A lot of people had questions about conversions and, how do you get better at word problems? What's a good strategy for word problems? I'll keep giving you guys tips with those, but mainly practice is going to help with that. And you start to recognize patterns. It's not something that I can give you a foolproof way. This is always how you do a word problem. And that's when it comes to this question in general, conversions always will trip you up if you're not careful. If you're not careful with your units, they still will trip me up if I mix up my units somewhere. And the longest conversion I personally have done, probably some of the ones that I've written for this class and for my Gen Chem class, honestly, because you start breaking up into smaller chunks as you go further along. And as you get further and further into science, you start needing to do conversions and units with calculus instead of just with algebra. And so that kind of changes how you answer the questions. And so it's not all considered one continuous conversion problem then. But that does turn into some of my grad school classes, some of the math heavy grad school classes. The final exam would be 3 hours long and it would be 3 questions. And I would get I might finish one of the 3 and I'd get about halfway done with the other 2. So there's like, you can make questions like really, really, really difficult. by basically not making assumptions like not neglecting wind resistance, for instance, is a big one in physics. But basically, as you get further and further into science, the word problems just get longer and longer, which also becomes more and more satisfying when you do understand them and you actually get a good answer for it. How well do you understand vaccines? You know, you get hit, you got poked, and then you don't get as sick anymore. Basically, what a vaccine does is it's kind of like a cheat sheet for your immune system. The way your immune system works is basically once you get sick, your body recognizes something as being an invader or an infection. It basically seizes on some distinctive characteristic of that infection or of that protein or of that virus. And then once it recognizes that, that kind of like spreads the message to the rest of your immune system. What a vaccine does is it takes a version of that illness that is no longer capable of infecting you, either can't reproduce or something like that. In case of mRNA vaccines, it basically uses your own cells, ribosomes, to produce some of the dangerous proteins to basically give your immune system. It's almost like a wanted poster with a sketch of a criminal on it. It's not really the exact infection, the exact bacteria or virus, but it's enough that your immune system can recognize it as soon as it shows up and prevent it from infecting more and more cells. It basically stops the infection before it gets going, really, before it reaches a critical mass. Gloria? Because sometimes those proteins that they inject you with to give your cells a chance to recognize them are still somewhat active. They're not active enough that they can actually reproduce and cause a full-on infection, but they'll still cause some of the symptoms, especially since some of the symptoms are actually caused by your immune system trying to kill the infection. One of the reasons that we get fevers is basically because if something is evolved to live at our body temperature, you raise our body temperature a couple of degrees, sometimes that's enough to actually kill off the bacterial infection. So a lot of times the symptoms are actually your body trying to fight against the infection, not caused by the infection itself. And so when your immune system kicks into overdrive because you just got a vaccine, you'll see some of those symptoms.
How long does it take them to like create the vaccine?
Well, I think everybody here lived through COVID, right? That was about as fast as a turnaround as you can possibly have in terms of a completely novel vaccine for a disease that's never had a vaccine before. And that was what, a year and change. When it comes to things like influenza, basically what they do is they take their best guess on what variant of the influenza is going to hit the US in any given year. And then they basically just throw that denature those proteins, and then they try to find some of those proteins that still have some of those characteristic structures that your immune system can recognize. So if it's a common illness like influenza, we can do it in about 3 to 6 months. Is a pretty good turnaround. If it's a totally new thing, then it can take a little bit longer. And if it's a really, really new thing, like we don't really have vaccines for fungal infections. Anybody here see the series on Last of Us? It's a zombie show, right? About infection from fungus. And they talk about how we don't have any vaccines for antifungals because we've never had a need to develop that. And it would be a totally different system that we would have to work out. So if it was something really out of left field, it might take years to actually get a working vaccine for something that was totally new. Any other vaccine questions? Vaccines are really, really cool. Immunology is really, really cool. I never took a class in that, but my wife and all my roommates were bio majors, and they all took immunology, and it was a really interesting class to learn secondhand from them. We'll save the black hole question for later, because once you get me talking about black holes, it'll be a while. But we'll talk about plastic real quick, because that's actually a pretty quick answer. Basically, plastics don't get broken down, but when something biodegrades, something's biodegradable, it basically just means microbes are capable of breaking it down and using those molecules. Plastics don't do that because they haven't been around long enough. They're too new. And so no microbes have evolved the right enzymes to be able to break them down, which is not actually strictly speaking true anymore. In the last 10 years, they've actually found some evidence of bacteria in landfills that had started to be able to break down certain types of plastics. So all of the old estimates that, oh, plastics are going to be around for 10,000 years before they break down, that's a chemical analysis. Like chemically, they're stable enough to be around for thousands of years. But sooner or later, evolution and microbes are going to catch up and be able and realize that that's a whole new niche that's never been exploited. And so that's going to give some new bacteria a really big head start because they're not competing with anything. So there's actually a big evolutionary driver towards developing enzymes to break down plastics, because that'd be really, really useful for a species of bacteria to be able to do that. In the meantime, they are also working on what they call chemical recycling, because plastic recycling really doesn't work very well right now. It's what's called physical recycling, where they basically just chop it up or they melt it and then they recast it, but it's the same molecules. They're working on chemical recycling, which is basically turning it back into the raw pieces that then you could use to make a new plastic from again. But we're not really all that close to that, because it turns out a lot of those reactions that we use to make plastics are pretty irreversible, at least if you're trying to do it economically. And as much as I want to talk about black holes, we're going to save that because we get to talk about quantum mechanics today instead. That's almost as good as black holes. Actually better, probably. More relevant to this class anyway. So quantum mechanics in general is kind of a scary term. Anybody heard anything about quantum mechanics before? Quantum? What does that mean? Small. Between atoms. We're talking about at the atomic level. When we're talking about these things, have you heard anything about quantum mechanics just in general? Jason?
It's got a lot to do with like electrons.
A lot to do with electrons. Turns out anything, when you get small enough, anything has the same basic principles that electrons do. But electrons in particular get studied in terms of quantum mechanics because they're the most common particle that's small enough that quantum mechanics matters. Basically, quantum mechanics always is happening, even at macroscopic scale objects, but it doesn't really matter. It's basically insignificant. It gets rounded off in the sig figs, basically. You have to get to something as small as an electron before a lot of these quantum mechanics ideas really take over. And one of the reasons, this is a really interesting picture. It was not originally colorized. Somebody went back in Photoshop and colorized this. Basically, this is the early 20th century was really, really interesting in science history because it was one of the first, it was the first time in history that you could get all of the experts in a field in the same physical location and communicate in real time. Until airplanes and steamships and trains and telegraphs, you really couldn't communicate in real time. If you look at a lot of the early chemistry and early physics research, it was done at what would feel like a snail's pace to us. Well, because you were relying on snail mail before there was even a postal service. Basically what would happen is I would write a paper and I would send it in a letter to somebody else in another country and ask them for their input on it. They would read my paper. They would get it a month later. They would read my paper, come up with some suggestions or some other ideas, send it back to me. It's now been probably 3 months at least since I sent it to them in the first place. And so all of the dialogue that was happening between experts was happening at that pace, where you would maybe get 2 or 3 exchanges per year. It wasn't until the early 20th century that you could actually get everybody in the same room. And this is far from everybody, but this is the biggest names. All of the bolded names on here. Everybody who who's got a box around their head, won a Nobel Prize. It's a lot of Nobel Prizes in one place. And this was from a conference in a place called Solvay in Europe in, I want to say this is the 1927 conference. And there's some really, really big names here. Everybody knows who that guy is, and everybody knows who she is, or at least by reputation, maybe. We got Einstein and we've got Marie Curie. The red boxes means they got their Nobel Prize in physics, and the green means in chemistry. And you can see that Marie Curie is the only one who has 2 boxes. She's one of only 3 people in history to win 2 Nobel Prizes. Can anybody name either of the other 2? They're not as commonly talked about. But one of my favorites is Linus Pauling, because he won a Nobel Prize. I think I might even have a picture of him later on, because he was sort of the second generation of quantum physicists. He won a Nobel Prize in chemistry, and he won a Nobel Peace Prize for his work in nuclear disarmament. And he's actually Northern California. He used to live in work at Caltech, I think, and then he moved to Big Sur in the 70s when all the folk rock singers were moving to Big Sur. So he got to hang out with Neil Young, and that's pretty cool. And he got really involved in nuclear disarmament and stopping nuclear proliferation. And so he won a Nobel Peace Prize for that. And the third one is a more modern guy named Barry Sharpless, that when you take OChem, you talk a lot about Barry Sharpless, because he had some really, at least when you take it with me, because I actually did some of my grad school research on one of the reactions that he studied. Good. Oh, that means that they didn't win one directly, but their students did. So let's see, that is that De Donder? Yeah, that's De Donder. And that is Fowler. Both of them had students who directly won a Nobel Prize. And some other interesting ones in here. Niels Bohr is one of my favorites. He's the one who argued with Einstein all the time. So Einstein didn't like quantum mechanics, and Niels Bohr is like, well, too bad, you're gonna have to live with quantum mechanics, because quantum mechanics seems to work. The other one that's worth mentioning is that one right there, next to Fowler, is Heisenberg. Heisenberg, I've never seen a picture of him where he didn't look like a little bit odd. He always kind of looks like a creeper. I've never seen a picture of him where he looks normal. I don't want to say normal, because normal is not the right description. And I thought that even before I knew that he actually was in charge of the Nazis' version of the Manhattan Project, he fought in hard to Hitler and Nazi ideology. There's a number of them in this picture that fell into that category at one point or another, but he was the worst. Who else is in there? Oh, the one sitting next to Marie Curie in the front row. He is a mathematician by the name of Lorentz. If you've ever heard of Lorentzian transforms. He also had an on and off romantic relationship with Marie Curie through most of their adult lives, once her husband died. So he was sort of like, he was also the old guard. Marie Curie and Lorentz were basically the generation before most of the scientists in this picture. But they were still alive and still very relevant. Lorentz laid the groundwork for a lot of the math behind quantum mechanics. And because we can't do this without, there's some good quotes about quantum mechanics. Niels Bohr, well, if you're not shocked when you first come across quantum theory, then you cannot have possibly understood it. It's gonna be weird. It's not gonna make any sense. Basically, our brains, just the same way we talked about how our brains only handle numbers between about 0.1 and 10. Our brains really don't understand quantum mechanics, because it goes against everything that our brains are evolved to perceive at the macroscopic level. We're used to dealing with things in a spectrum where you can have You know, I could pick a point anywhere along this ruler and measure what that is, and I could get infinitesimally smaller, right? Quantum mechanics basically says you can exist at 19 inches or 20 inches, but not in between. Which is weird. Again, it's not something our brains are evolved to handle very well. All right, so let's talk about how that works again. And this is also a good another reason why I like doing this one is because I get to bring in an electric guitar, because music theory actually has a lot in common with quantum mechanics, the way these behave. Right? Does anybody play a stringed instrument in here? Any guitar players, violin, anything with standing waves? Kind of. What do you play? Guitar? You know what a harmonic is? Not a harmonica, a harmonic on a guitar string. Have you heard of that before? All right, well, I'm going to demonstrate harmonics real quick. All right, so the basic principle of a guitar, I use electric guitar partly because I just like electric guitars better, and partly because it actually demonstrates this phenomenon better. All right, so the way a guitar works by vibrating a string. An electric guitar works by picking up these, there's magnets here in the guitar pickups. And when the string vibrates, the magnets vibrate with it, and that generates an electrical current, which then gets passed through the cord to an amplifier. So the easiest way to do that is I'm just using my fingers to mute all but the heaviest string here. It's just vibrating back and forth. If I want to change the pitch of that, I can push down on the string, any one of these frets, and that just makes the wave shorter. When you make the wave shorter, but with the same heaviness of the string, it will vibrate at a shorter wavelength, a longer frequency, bigger frequency. However, if I want to actually make it vibrate at a different frequency without just shortening the wave itself, I didn't bring a pick today, unfortunately. You can do that by basically adding a spot to the middle called a node, where it doesn't vibrate. So if we want to increase the frequency, you can do that by shortening the wavelength, or you can add a node in the middle. And that cuts the wavelength in half. If I put my finger exactly halfway down the length between here and here, at that point where you're halfway, you can create a node. So I bumped it. And what that does is it cuts the wave in half. You shorten the wavelength. I can't just do that anywhere though. I can only add a node if it's going to create something where both ends of the string are still stationary, where both ends of the string still hold still. So I can do that at halfway. Where else could I do that? A quarter. If I can do it at a half, I can do it at a quarter. Corresponds to the 5th fret on a guitar. And then you don't even have to hold your finger down. For any of these other spots, if I push the string down to shorten the wavelength, sorry. If I take my finger off, it stops vibrating. By doing it on a node, we're actually creating this standing wave where both ends are still just as far apart as they were. But you can only do that at even fractions. And basically, if you get too far away from even fractions, even that won't vibrate enough, won't have enough of an amplitude. So you can do it at a half, you can do it at a quarter. So here's a half. There's halfway. I can do it at a quarter, and I can do it at a third. but I can't do it at just some random distance. If I try to do it at some random distance, nothing happens. It doesn't vibrate until I get it the right distance. So the reason that this applies to quantum mechanics is just like with this ruler. With this ruler, when I said, okay, you can't be 19 and a half, you can only exist at 19 or 20. That's the way electrons behave, and it has to do with the frequency of the electrons and the energy of the electrons. When your electrons it's not that they can only exist in certain spatial places, they can only exist at certain energies. Just like the guitar string can only vibrate at certain frequencies. All right, so I've got some more figures and some more analogies. What I want, and I will frequently refer back to remember on the electric guitar, remember how we talked about that? The danger with analogies when it comes to quantum mechanics is that none of them are perfect. So we always run the risk when we're using analogies of trying to take the analogy too far. So if you come up with good what if questions, like, well, what about this? Like, well, then that's actually just that I took the analogy too far with that one. So bear with me in that case. And I usually have other analogies we can talk about. All right, so, and when we shortened up the wavelength, that corresponded to having a higher frequency or higher energy. Another analogy that gets used a lot in quantum mechanics is basically you can think of the different energy levels as sort of distance from the nucleus. These electrons can exist at certain distances from the nucleus because different distances correspond to different energies. And the analogy we use to talk about that is kind of like bookshelves. We can all agree that if we're talking about gravitational energy, the higher up you put a book on a bookshelf, the more energy it has. If it fell off the bookshelf, it would fall farther, right? And have more energy by the time it hit the ground. But you can only put so many electrons on each energy level, on each bookshelf. And if you want it to be stable, you want to start from the bottom and work your way up. You can picture building a bookshelf and putting it in the middle of the room, not a particularly stable one. If I put a whole bunch of textbooks on the top shelf and then we had an earthquake, what's going to happen? The whole thing's going to fall over, right? If I wanted to stay stable, I would start by putting all the weight in the bottom first, right? Fill up the lowest energy levels first. And then once they're filled, you can move up from there. And then it might actually withstand an earthquake without falling apart. All right, and we can think in terms, it's not just distance from the ground in terms of electrons, it's actually distance from the nucleus. Because what charge does the nucleus of an atom have? Not a number to it, just like, is it positive or negative? Positive. And electrons are what? Negative. And what do positives do to negatives? They attract, right? So just like the gravitational attraction between textbook and the ground, there's an attractive force between electrons and the nucleus. And so that means that they're always going to try to be as close to the nucleus as possible. But then what does that mean about, see, do I have my slides out of order? No, I think I just didn't talk about this for a second. So then one of the questions that frequently gets asked then is, well, if I have a positive charge on the nucleus and I have electrons around it at certain energy levels, what's to stop the electron from just falling all the way to the ground, to the nucleus? We're going to get to orbitals. Orbitals are basically a fine tuning of the idea of energy levels. So these electrons can exist at these different energy levels in these different orbitals. Why wouldn't they just, if they're attracted to the nucleus, why wouldn't they just stick to the nucleus? Anybody have any ideas?
Do they like cancel out like that?
They don't. The charges would cancel out if they did that. But it's actually even weirder idea? Has anybody heard of the reason that Heisenberg is in this picture? Is for what? What is Heisenberg known for besides being a Nazi? Breaking Bad. True. Actually, if you know Heisenberg's full backstory, Walter White picking Heisenberg as his alias actually is a lot of foreshadowing for, you know, the whole fall of Walter White. The Heisenberg uncertainty principle. Who's heard of that? Ish? No? Okay. The Heisenberg uncertainty principle, basically, it has to do with uncertainty, just like with our measurements. The Heisenberg uncertainty principle is the uncertainty in a particle's position. We use the Greek letter lowercase sigma for the position times the uncertainty in its momentum, the Greek, which is T in physics, has to be greater than or equal to a constant, which I believe is h bar over 2. It doesn't really matter what it is. It's a constant number, which what this really says is that when you get something small enough, you can't know its position and its momentum exactly. And the more accurately you know its position, the smaller your uncertainty in the position is, the greater your uncertainty in its momentum is. Basically, you can't know where something is and how fast it's going at the same time. That means that electrons can't just fall to the nucleus, because that would be violating the uncertainty principle. Because you would know both that it was moving at the same speed as the nucleus and that it was sitting right on top of the nucleus at the same time. You can't know both of those things at the same time. That's not how the universe works. Does anybody have math class where you talk about boundary conditions? You have to wait till you get to calculus for that. Oh, more upper division calculus even. Basically, this idea is not really a theory. It's more of a law. It's just that at this point, the only way we can explain it is it's basically just how the universe behaves. This idea you can't know both of these things at the same time. And one of the ways you can think about it is they actually use the uncertainty principle, or the what do they call it? They use the same concept in anthropology. You can't observe the system without disturbing the system. If you wanted to observe something, by nature of observing it, you change the system.
So like Schrodinger's cat.
Schrodinger's cat.
Okay.
Exactly. And again, I can't think of the term that they use in anthropology. Is, let's say we've got a tribe in a jungle somewhere who's never come in contact with the outside world. An anthropologist is trying to study their culture. By studying them, he or she is going to change that system. Even if you're trying not to change that system, it might be something as simple as they see a footprint. You're trying to observe them from hiding, and then later they find a footprint, and now all of a sudden they like, what kind of creature is this that has a boot with treads on it? That's something they never would have encountered before, right? So by observing the system, they change the system. The same thing happens with electrons. Asen?
And I think I saw somewhere online that like electrons are functionally this clouds of randomness and don't be able to tell. Is that true?
Kind of. So the only way we have of observing where an electron is by shining light on it. The problem is, by shining light on it, the light itself carries enough energy and the electrons are small enough that if a photon bounces off of an electron, it'll change the electron's path. So the analogy I use for that, let's say that we hung a baseball from the ceiling on a string. We turned out all the lights and it's pitch black, and I'm trying to find that baseball, figure out where its position is by throwing golf balls at it. As soon as I hit it with a golf ball, I could determine, okay, I heard it hit right there. I know exactly where it was, but now it's moving. If I did something like measure its speed, the act of measuring its speed is going to change everything as well, right? Maybe I measured its speed by putting my hand out and letting it hit my hand. And then I can say, oh, it hit my hand pretty hard. It was going pretty fast. But now all of a sudden I don't know how fast it's going anymore because by hitting my hand, it changed the system. Diego?
If you hit the baseball with the golf ball, you just wait until it like settles down, or is it just gonna permanently change how it moves?
It's going to permanently change how it moves to some extent. If we're measuring with enough sig-figs, and that's where macroscopic examples start to fall apart a little bit, because yeah, we know we could just wait for it to stop again if we waited long enough. But electrons don't have air resistance the same way that the ball does. There's no friction with electrons. And so the electrons, by measuring them, we're permanently changing the system. Jason?
So basically, they're just so small that we're so big that just looking at them basically changes everything.
Exactly. Exactly. So not only can we not know where they are and how fast they're going at the same time, they can only exist at certain energy levels, and they don't exist in any one particular spot until we observe them. So that's what the bookshelf analogy is also not great, because the books are discrete objects. It's more like if we put a ping pong ball bouncing back and forth in this shelf that never would slow down. If we said there was no wind resistance or no air resistance, that ping pong ball is just going to bounce back and forth forever. Where is the ping pong ball at any given point? Well, it's on that shelf. But I can't actually measure exactly where it is on that shelf without changing the system. All right, and so one of the ways, like I mentioned, one of the ways that we actually measure anything about these electrons and these energy levels is by shining light on it. So this is one of the first experiments that they started doing to show how that actually, this is actually what Einstein, part of what Einstein won his Nobel Prize for. He actually didn't win a Nobel Prize for E equals MC squared. He won a Nobel Prize for figuring out that light exists as photons, not as just waves. It actually exists as particles. And one of the ways that he figured that out is by basically shining light on an object and looking at what light was absorbed and what that object did. So if you shine the right wavelength of light on an electronic system, it's the equivalent of taking one of these books and moving it up an energy level, moving it up a shelf. You can what's called promote an electron by shining light on it. When you shine light on an electron and you promote it from one energy level to the next energy level, that photon, that light gets absorbed. That photon disappears. Basically, the photon ceases to exist and it's converted entirely into the energy needed to move an electron from a lower energy level to a higher energy level. The same thing happens when the same but opposite happens when electrons relax. When they relax, that's when they go from a high energy level and they drop down an energy level. And that has the exact opposite effect. Same way that a photon is destroyed, it ceases to exist. When you promote an electron, you actually create a photon when electrons relax and fall down an energy level. That's actually how LEDs work. LEDs work by applying a voltage and current to promote electrons to a higher energy level and then letting them fall back down. When they fall back down, they give off light. And the wavelength and frequency of light that's given off is based on how big of a gap you have between your energy levels. So go back to the bookshelf analogy. What's the difference in energy between your lowest energy bookshelf and your next bookshelf? You have to put a certain amount of energy in to get the book to move up a level, right? You can't put in just part of the energy. You have to put in all of the energy. Right? And so when that book falls, then it's going to give off as much energy as you put into it. right? And the different wavelengths of light that we get correspond to what that material is. Somebody asked me a question on the quiz a couple of weeks ago about how do we study other planets and stars, right? I think we talked about it. Basically, we can, by looking at what kind of light is given off, we can tell what atoms must be present because we put it through a prism, we get something that looks like a barcode. It basically is a barcode, except instead of it being a number in binary, it's giving you what wavelengths of light can that object give off. And the different wavelengths of light that it can give off correspond to different elements on the periodic table. All right, and somebody mentioned the word orbitals earlier. So orbital is basically another way of thinking about these energy levels. Instead of calling them bookshelves or energy levels, basically orbitals are the different energies where an electron can exist. So just like with the guitar, only certain frets, only certain fractions of a string would actually give us our harmonic, right? Only certain energies are places where the electrons can exist. And we call those, there's a couple ways of levels of detail describing them. Energy levels is a pretty good way, but then within each energy level, there's also what are called orbitals. And the different orbitals just correspond to different functions, different shapes, basically where you're likely to find those electrons. And you don't really have to memorize how these work because the periodic table has this information for you. In your first energy level, you can only fit 2 electrons. And the way that corresponds to the periodic table is your first row of the periodic table has how many elements in it? 2, just hydrogen and helium. The first row of the periodic table corresponds to putting electrons into the first energy level. When you get to the second row of the periodic table, how many elements are in the second row of the periodic table? There's a total of 8, right? From lithium over to neon. That tells us that the second energy level can hold a total of 8 electrons. It gets a little bit trickier after that because we actually have to talk about the structure of the orbitals for a second before it'll make much sense. But basically, if we want to figure out where the electrons are and what energy they have, we talk about what energy level they're in. And so this is what's called a electron or an atomic orbital diagram, where basically we figure out how many electrons we have, and we figure out what energy level they're going to go in. Where are we going to fill it up? So we talked about something like sodium. Sodium has a total of 11 electrons. If it has 11 electrons, we need to find a place for all of those electrons. They can't all go to the lowest energy level. There's not space for them. So what we do is we just basically start adding electrons into energy levels until we run out of electrons. We're never going to run out of energy levels because there's always a higher energy level we could get to. But we can only put 2 electrons in the first energy level, and we can put 8 electrons in the second energy level, which leaves us with 1 electron left. That 1 electron would go into the third energy level. Right? And this is an okay way of looking at it. It doesn't make a whole lot of sense. It seems kind of arbitrary until we talk about why does the second energy level have 8 electrons? Basically, every time you go up an energy level, you add a new type of orbital, a new type of room where you can put the electrons. And there, as you get higher and higher in energy levels, it gets harder and harder to put the electrons into these higher energy orbitals. And so we only put we only start putting electrons into these higher energy orbitals once we've filled up all of the more stable orbitals, just like our bookshelf. So if we were going to actually draw this diagram out, I guess I should also define these arrows are representing electrons. So it turns out in order to describe an electron, you have to have 4 numbers to fully describe where an electron is. Has anybody heard of string theory? String theory's kind of fallen out of favor with theoretical physicists, but it's useful in that it gets people used to the idea that there's actually more than just 3 dimensions. Basically, a dimension is just any variable that you use to describe matter, where something is at any given time. Electrons have more than just 3 dimensions because you have to describe them using 4 variables. The simplest variable is what energy level is it in. That's what's called the principal quantum number. What energy level is it in? And I'm not going to ask, I might ask you. The principal quantum number is what energy levels is the electron in. And then within that, you also have to describe what type of orbital is it in. The type of orbital we describe with, let's see, is that I always forget the names of the other quantum numbers. They're not as important. But basically, it's orbital type. The angular momentum quantum number, maybe? And every orbital has distinct characteristics and shapes that are based around, just like with the electric guitar, how many nodes does that function have? So this first energy level, the shape of this first orbital basically just looks like a sphere. If you're trying to figure out where the electron is in this first energy level, we're just gonna say it's somewhere inside this ball. We can say with a fair degree of certainty. But as you start going to higher energy levels, this is what's called an s orbital. And an s orbital can only hold 2 electrons. When you add a node to it, though, just like with the harmonic on the guitar, we add a spot where we can't find the electron, where there's 0 probability you will find the electron. And we call this a p orbital. A p orbital basically looks like a figure 8, except in 3 dimensions. It looks like 2 balloons. If you picture taking 2 balloons and holding them together by the knot, it would kind of look like a figure 8 in 3D. Can you picture what I'm describing there? Well, there's actually 3 different ways we can arrange a p orbital. You can put it along the x-axis, you can put it along the y-axis, or you can put it along the z-axis if we're in 3 dimensions. So there's actually 3 places we can put electrons, and each of those orientations can hold 2 electrons. So the second row of the periodic table is 8 elements across, because the second energy level has 1 s orbital, and then it has a p orbital. So the second energy level can hold a total of 8 electrons, because it's a combination of an s orbital and a p orbital. And every time we go up another energy level, we add a new type of orbital. And this third energy level, we can have what's called a d orbital. And d orbital almost looks like a clover leaf. Picture like the 3-dimensional figure 8 that I was describing, except now with 4 lobes to it. Where each of those is kind of balloon shaped. And that just means that if it's in a d orbital, it's gonna be somewhere in this shape. So just like the functions started looking more and more complicated, when I added more and more nodes on the guitar string, the functions start looking more and more complicated the higher energy level we get to as well. Right, and so what that leads to, this is basically a better, more detailed drawing and color coded of exactly what I have on the board here. Every energy level has an s orbital. Then when you go up from the first energy level to the second, you add a p orbital. So your second energy level can hold a total of 8 electrons. And then when you get to the third energy level, you have an s orbital, a p orbital, and a d orbital. But how come if we look at the periodic table, how come this third row of the periodic table only has 8 elements in it? Well, that's because if you look closely at the energies here, that 3D is actually higher in energy than the 4s. So we actually don't put electrons into that 3D orbital until after we fill up the 4s. So let's do a practice. If we're going to fill this, let's leave out the d orbitals for now. If I wanted to know the electron configuration of, say, oxygen, how many electrons does oxygen have? Total of 8 electrons when it's neutral, right? If I want to know where those electrons are, I basically just start at the bottom and I start filling in electrons until I get to 8 electrons. Each of these lines represents a different energy that can hold 2 electrons. And we usually draw them as arrows, and we draw them in opposite directions because actually the fourth quantum number that I didn't really define yet is called spin. Basically, the electrons can be, they're not really spinning, but the math looks like a sphere rotating. And a sphere can rotate with the same energy in 2 different directions and still have the same energy in it, right? So like if I spun a coin, if I was trying to spin a quarter on the table here, I could spin it clockwise or counterclockwise and give it the same amount of energy, right? So there's every one of these different energies can hold 2 electrons, one spin up and one spin down. They use up and down rather than left and right because they don't want you to think it's actually physically spinning. And plus we're used to thinking as up and down as being energy, the y-axis being energy, so it's easier to describe it this way. All right, so if each of these lines can hold 2 electrons, go back to our example. We're trying to write the electron configuration for oxygen. We can put 2 electrons into the first energy level, and then it's full. We still have 6 electrons left, right? It's basically because of that rotation. It's not really, again, they call it spin, except it's not actually spinning, but it's, you can have 2 electrons with the same energy as long as they have opposite spin. They can both be in the same place at the same time. The analogy I use for that is it's kind of like if you had they call it hot bunking on submarines. You don't need as many bunks as you have sailors on a submarine. You just need enough that half of your crew can sleep at any given time. Because as soon as one person leaves, someone else can go share that bunk. Right? So because they have opposite shifts, they're able to occupy the same space. They can't be in the same space at the same time, but they only need 1 bunk for 2 sailors if you do that. Spin is kind of like that. As long as they have opposite spin, they don't really interact because they have different shifts. So if we have 6 electrons left, we're just gonna go to the next lowest energy. We filled up our lowest energy orbital, so we go to the next energy level. So an n equals 2 also has an s orbital. So we can put 2 electrons there, one up and one down. Are we done yet? We still have 4 more electrons, right? Where are we gonna put them? The next in the 2p. So the 2p can hold a total of 6. We only have 4 left to go. Basically, you just add electrons in. You add when they're all the same energy, you put 1 electron into each spot before you make them start doubling up. You're not going to have people sharing a bed on a submarine until you run out of beds, right? You don't double up until they're all occupied by at least 1 electron. Okay, so this is what we describe as the electron configuration of oxygen. So we don't want to have to draw this out every time. So we have a shorthand for it. The shorthand is all we do is we say what energy level is it in, what type of orbital, and how many electrons are in it. So the first energy level has an s orbital with 2 electrons in it. Then the second energy level has an s orbital with 2 electrons in it. What's the last thing I'm going to write? We still write the 2 to make it explicit. We're talking about the 2p, but then, yeah, 2p4. When you know the rules for drawing this, this has all the information you need to get to this. Why does any of this matter? Because it turns out things like being able to predict that there's 2 unpaired electrons here winds up being really, really important. These unpaired electrons are actually what are responsible for magnetism. Magnetism occurs when you have unpaired electrons with the same spin. When you have unpaired electrons with the same spin, they generate a magnetic field. Say it again. Oxygen does have a magnetic field. You can't see it when it's a gas, but if you have liquid oxygen, you can actually pour it in between the 2 poles of a magnet, and you can actually watch it bend. The stream will bend. It looks like it's a liquid, right? So you pour it, and then as it's falling down, it'll actually curve to follow the magnetic field. How do you get liquid oxygen? Get it really cold. We'll talk about phase change in more detail, but basically anything can be a liquid if you get it cold enough. All right, so those are our rules for writing out our electron configuration. When I say write out electron configuration, this is usually what I mean is the shorthand. I'm not going to have you draw this every time. We have a whole lab for next week that's just going to be lots of practice where you draw this out and then convert it to this. And you can do that as long as you can follow the periodic table. And because the periodic table has all of this information in it. Does anybody know what those different parts of the periodic table are called? Why there's like those 2 columns in the front, and then there's that big gap, and then there's 6 columns off to the other side? This is called the S block. This is the D block that we'll get to in a second. This is the P block. If we want to write the electron configuration for oxygen, all we really have to do is count along this periodic table until we get to oxygen, until we get to the right number of electrons. We're in the first thing we do is we're in the first energy level, so you write a 1. We're in the first row of the periodic table, so you write a 1. We're in the S block, so you write 1s, and there's 2 electrons you can fit in that first row of the periodic table, so you write 1s2. Then you go to the second row of the periodic table. You're back to the S block. So now we're in the second row, so we write 2. We're in the S block, so we write S. And there's 2 elements until you get to the end of the S block. And then we jump across the P block. We're still in the second row of the periodic table, so it's still 2. We write P because we're in the P block. This 6 elements on, or the 6 columns on the far right are labeled as your P block. On the periodic table that you'll have on the test, and I think on these new ones, they have blocks labeled. They don't.
On the bottom.
Oh, on the bottom, perfect, thank you. And then to get to oxygen, we only need to count 4 spots over. So 2p4. Alright, so if you may have seen it written out as a diagram before, as like a triangle. 1s, 2s, 2p, 3s, 3p. Has anybody seen this before? Okay, then good. Don't worry about it, because I don't like this. I like that better. Because you'll always have a periodic table. Yeah.
Every single like periodic elements are one atom.
Everything other than hydrogen starts with 1s2. Because even helium has 2 electrons, right? There would be no 2 anything for helium. It would just be 1s2. All right, so why does the d orbital get weird? Well, let's look at. So let's look at aluminum. Let's do aluminum. What would the electron configuration be for aluminum? We need 13 electrons. We can still use this. You can use the periodic table, or you can use this here. We're going to start by putting 2 electrons in the 1s. So it'll be 1s2. Then we're in the second row of the periodic table. Still in the s block, and it can hold 2 electrons. Still in the second row of the periodic table, but we jump to the p block. 2p, and p block is 6 elements across, so we can hold 6 electrons in it. Another way of saying that is it's got 3 lines, and each line can hold 2 electrons. Now we're in the third row of the periodic table. What's the third row of the periodic table going to do? Still an S, can still hold 2. We're almost there, right? We're still in the third row of the periodic table. Jump to the P block. We're just counting along with the atomic numbers. There's only 1 electron that we need to put into the P block. If we add up all these things that are written like exponents, it will add up to 13 because there's a total of 13 electrons.
Wait, so if there's only 1 arrow, does that mean it might be like?
Exactly. Yeah, aluminum actually is very slightly magnetic. It only has the 1 unpaired electron. And so it's not as magnetic as other things. If you know, most of the strongest magnetic elements are down in the very bottom or in the D block, where they can have lots of unpaired electrons because of how big the D orbital is.
So is it like based on how many unpaired electrons there are? So if
Yeah.
there's 3, it's more magnetic.
Correct.
When the periodic table was invented, was it so you could find the electron configuration?
No, that's a side effect. They have organized it based on putting all things with similar properties in the same columns, but the side effect of that was they didn't realize it at the time. They were arranging them based on their electron configurations. Because what would boron look like? Oh. All right, Minnesota in-laws have been around. Thanks for that. Oh, geez. My 2-year-old started mimicking my mother-in-law last week. Oh, jeez. What would boron's electron configuration look like? It's going to be really similar to aluminum. 1s2, 2s2, 2p1. Boron and aluminum actually have a lot of similar properties because They both have one electron in a p orbital. They're not identical because it's a 3p1 versus 2p1, but they have similarities because of that. In column 17, fluorine, chlorine, bromine, iodine, they're all going to be something p5. They're going to have similar properties because their electron configuration ends in p5. All right. Let's talk about gallium then. We know it's going to end in 4p1. But if we're following this chart here, this is where something weird happens. Because after we fill up the 3p, everything about gallium is going to be the same as aluminum. 2p6, 3s2, 3p6 now. We're trying to get to gallium. Then we jump to the fourth row of the periodic table. So we're in the fourth energy level in the S block, and it can hold 2 electrons. Because even though the third energy level has a d orbital, the d orbital is actually higher in energy than the 4s. So when we look at this graph here, we're trying to fill from the bottom up to make it as stable as possible. So we actually get to 4s before we get to 3d. So even though the first part of the d block shows up in the fourth row of the periodic table, it actually technically belongs to the third energy level. So after we fill up 4s2 for gallium, we go to the d block, but it's 3d. We're offset by 1 row because of this difference in the energy. And how many electrons can you fit into a d orbital? 10. If you count across the periodic table, count across the d block, it's 10 elements across. And then what's the last thing for gallium? Now we're in the p orbital or p block in the fourth row, and it can hold 1 electron. Right? So your d orbitals are always just going to be offset by 1 row because they're actually higher in energy than the s orbital for the energy level above that. Right? So your electron configurations for the d block elements, the transition metals, get a little bit weird because the d block being so big, and if you might notice this isn't done perfectly to scale, but as you get further and further up in the energy levels, they actually get closer and closer together. Going back to the guitar string analogy, I could cut the guitar string in half to get a harmonic, or a third, or a quarter, or an eighth, but all of those start getting closer and closer together the higher energy you get. So at these higher energy orbitals, they all start getting really close together, and you wind up with other things, other variables that wind up affecting this, like magnetism. So basically, I'm not going to ask you to do an electron configuration for anything from the d block, unless it's the very end of the d block. Because we can, if we know that it's the end of the d block, we know what its electron configuration is going to look like because we can fill up the d block, the d orbital completely. All right, last note. I realize I haven't given you a quiz on element names yet. Should probably do that so that we can all look at that. And when I say gallium, everybody knows I'm talking about Ga. So week from today. Sorry, week from tomorrow. It'll be on a Tuesday. You're going to take elements quiz. It'll be the one and only time that you have to put away your periodic table. Go take it in the library. Where there are no periodic tables. And it's all 118 elements. You don't have to memorize where they are on the periodic table. You just have to be able to put their atomic symbol, their 2-letter abbreviation, to the name and back again. Or not back again, but both directions. I'm not gonna ask you about every single one. I'm gonna pick 30 of them. Madison?
Marks off, we can't like spell them correctly.
Those are always the first two questions. Really, all 118? Yes. And then am I gonna mark you down for spelling? Not as long as you're close. If a reasonable person could read what you wrote and get to the right name, then I'll call it good.
No
No polyatomics.
poly.
We'll do polyatomics, be your next closed book quiz.
How many polyatomics do we have to memorize?
There's about 30 of them. Somewhere between 24 and 30, I can't remember exactly. But they're mostly all related to each other. All right, week from Tuesday. Elements quiz. Have a good one. Bring your computers tomorrow and Wednesday.